Hello, Astronomy. Welcome to section 12.5. Trying out a new tech setup, so it might look a little different, it might sound a little different. Obviously, you can see on the sides here that parts of the video are still not. Whatever. 12.5, we're talking about white dwarfs, we're talking about pulsars, we're talking about neutron stars, we're talking about X-ray bursters and novas and stuff like that. So just continuing the stuff that we've been learning, all the weird stuff. What happens after a star dies? How does a star die, and maybe can that do anything after? And the answer is yes, it can. That's what we're going to learn today. As soon as I figure out, there we go. That's what we're going to look at today. I have the book open to the wrong page, but now it's in the right spot. So it says white dwarfs and pulsars in closed binary systems can become nova, bursters, and supernova. So we already looked at what happens in a supernova. We already know what white dwarfs and pulsars are. We don't know what nova or bursters are, though. So this is a new word, and this is a new word. And in case we don't remember, white dwarfs are what happens when a smaller star runs out of fuel. He throws off all of his outer layers, essentially, and it's just the hot core that's mostly carbon. Just out there, it's not generating heat, it's just releasing heat that it had when it was a star. And then once it runs out of that heat, it's going to be done shining, and it's just going to be a ball of carbon floating out there. We talked about pulsars. They are neutron stars from the bigger stars. When the bigger stars die and they explode in a supernova, they make a neutron star. And we know that if the neutron star is spinning and has that magnetic field, then it's a pulsar, because it looks like it's pulsing radiation at us, when in reality it's just spinning so fast that only the part that is shooting out the radiation hits us only every once in a while. Okay, so that covers these three words. Supernova is the explosion that makes the neutron stars that make the pulsars. We know the white dwarfs are the dead, old, regular stars. We don't know what these two words are. So let's go ahead and begin. Explosive hydrogen fusion may occur in the surface layer of a companion white dwarf in a close binary system, producing the sudden increase in luminosity that we call a nova. So a couple jumps here I feel like already that it makes. It's expecting you to remember what a white dwarf is, which we just talked about. Hopefully you guys remember what a binary star system was. That's when there are two stars orbiting each other. And hopefully you remember that luminosity is like a measure of brightness. A nova gets it increases the luminosity by a factor of 10 to the 8th, 10 to the 4th, in between there, 10 to the 4th and 10 to the 8th. Whereas a supernova, when a star actually explodes, a supernova gets up to 10 to the 9th times brighter. So a nova is still incredibly bright. It's just not as bright as a supernova. So that'll be important to think about. Almost like a supernova is brighter, you just think of the word super as in front of there. A nova's brightness is followed by a gradual decline that may stretch out over several months or more, and every year 2 or 3 nova are observed to flare up in our galaxy. So that happens enough for us to notice them. We also assume that there's a couple more. It's just that we can't see everything in our galaxy. There's a lot of dust clouds and stuff that might prevent us from seeing that. So let's further categorize the difference between nova and supernova. First off, let's go back to what we were talking about last section. Supernova. That happens when the core collapses in a pretty big star, right? That type of supernova is actually called a type 2 supernova. Okay, so the ones we learned in 11.4 and 11.3, when the star runs out of fuel, all the material comes rushing into the core, squishes it into a ball of neutrons. That is a type 2 supernova. And if they bring up type 2 supernovas, that means there has to be a type 1, right? Like if that's the second type, that means there is a first type. And the first type is known as a type 1 supernova. There's actually a couple different kinds of type 1 supernova, but we're just going to go over type 1A, I believe. Type 1 supernova results from an accreting white dwarf in a close binary star system, which becomes a supernova when carbon fusion ignites explosively throughout such a degenerate star. Okay, we have to remember what all these words mean. So this supernova, results from an accreting. Accreting means they are gathering mass. So an accreting white dwarf, so a white dwarf that is gathering mass, in a close binary star system. So this white dwarf that is gaining mass is next to another star. Okay? So it results from a white dwarf that's gaining mass from a close star, which then becomes a supernova, which means it then explodes once it gathers enough material for carbon fusion to take place on the inside of that white dwarf. Remember, the white dwarf is not undergoing fusion at all. The white dwarf is just really hot from what it used to be. But if it's next to its friend, and its friend is giving off a bunch of material, and the white dwarf is sucking up some of that material, it's possible that the white dwarf can get so much material in such a short amount of time that it gets way too much material at once, and it reaches right here what it says a critical mass. Okay? So the white dwarf is sucking up the material from the companion star, and eventually it gets to some type of critical mass. What happens then is that in the center, there's actually thermonuclear reactions that start happening. There's so much heat and pressure on the outside that it compresses the inside to actually start fusing. Now, we talked about the fact that this is degenerate, meaning normally when you heat stuff up, it expands. Since this is degenerate matter, it's not going to expand when you heat it up. So the only thing it's going to do is just heat up even faster. So it heats up even faster and faster and faster until we see here, the flame spreads outward from that core, converting oxygen and carbon into radioactive nickel. And then within a few seconds, the dwarf has been completely destroyed. Over the following weeks, as the radiation kind of calms down, the glow kind of decays. I'm sorry, I read that wrong. Over the following weeks, the radioactive nickel decays, which gives off the glow. Because as radioactive elements decay, they give off energy. Sorry, brain fart, I read that wrong. Okay, so we just saw the white dwarf explode here. It gathered material from its friend, gathered so much that it compressed and heated the core so much that the carbon was actually able to start fusing. Since that matter is degenerate, it could not expand when it heated, so instead it just heated up even more. And it heated so fast that within a few seconds, the white dwarf blew itself apart. So the question is, if a white dwarf has no actual energy source, where does it get the raw material? Hopefully you guys followed along with what I just said. Can only do that if it's friends with another star in a binary star system, and if it's actually able to draw that matter in from that star, thanks to its gravity. If they're a little too far apart and it's not grabbing that much material, then we'll see what happens. But this has to be, they have to be pretty close and be able to suck up enough material for this to kind of suddenly happen. So if we're comparing supernova, a type 1a and a type 2, it helps to look at this graph that this slide is talking about, a light curve, a graph that shows the brightness of a supernova versus time. And in both cases, the type 1 and type 2 supernova, it begins with a sudden rise in brightness that occurs in less than 1 day. So in less than 1 day from the beginning of a supernova, the brightness increases by a lot of whatever it originally was. Here we see a type 2, that's the one we learned about last week. Here we see type 1a, and that's the kind that we're learning about right now. So they both reach their maximum brightness in about a day, a little less than a day. And then after that, we see that they gradually lose their brightness. Something I want to point out about math is that once we get to these 2 points, this is a shallower curve than this, which means the type 1a supernova gets brighter and then it decays faster than the type 2 does. Type 2 doesn't get as bright, but it doesn't decay as long. I'm sorry, it decays longer. It takes a longer time for it to not be able to be seen anymore. So this is just talking about brightness. I do want to point out that the type 2 supernovas are still releasing a lot more energy. It's just that the type 2 are releasing a lot of those neutrinos that we talked about, those super tiny little particles of mass that can fly through things. Type 2 are releasing a lot of those that don't really contribute to the brightness, but it does contribute to the energy. Type 1a does not get rid of a lot of those. So type 1a is all flash and no substance, and type 2 has both flash and substance, if that kind of makes sense. So if we look at that graph again, which is brighter, a type 1a or a type 2 supernova, hopefully you guys can realize if this is luminosity, type 1a is definitely brighter. And then which has a longer lived brightness, a type 1a or a type 2 supernova. Once again, looking here, which one of these will last longer? Well, I already said this one has a shallower curve, so that will last longer. So type 2 supernova have a slower brightness decay rate. They never get as bright as a type 1, but they stay what light level they have for a longer time than the type 1a have. So those were supernova we were talking about. That's when the star completely blows up. But this chapter started with talking about a nova, which was just that increase in brightness. So let's look at what that is now. We know what a supernova is. Now what is a nova? Well, all nova are closely orbiting members of binary star systems containing a white dwarf. So far it's kind of sounding the same what we just talked about. However, in this case, supernova are the result of a white dwarf accreting so much material that nuclear reactions happen on the inside of the white dwarf. That's what we just talked about. But nova, on the other hand, undergo nuclear reactions on the surface of the white dwarf, where the material gathers. Do you guys see the difference there? A supernova, and at least in the context of what we're talking about, a type 1a supernova results from when a white dwarf gets so much material from its friend that it kicks off nuclear reactions on the inside of the white dwarf and blows itself apart. A nova is just when that white dwarf gets some material from its friend, only enough to squeeze the material on the outer layer of the white dwarf and cause the outer layer of the white dwarf, all the stuff that it gathered, to undergo some nuclear reactions. So in a nova's case, the star is not blowing itself apart. There's nothing happening in the core of the white dwarf during a nova, but the core is blowing up in a white dwarf during a supernova. Here's some examples of these binary star systems. Semi-detached binary, we have a large star and a small luminous main sequence star here. We have a semi-detached binary with mass transfer. And then we have an over-contact binary where they're about the same size. These pictures just show their brightness. So when we're looking at a nova, the material from a friend star, like here, is being put onto the surface of a white dwarf, but it is not enough to squeeze the white dwarf into undergoing fusion in its core. Instead, it's only enough to squeeze itself, the outer layers itself, to only make the outer layers undergo some fusion. So this star is spitting off hydrogen. The hydrogen gets stuck on the surface. And what happens is that surface hydrogen gets squeezed by the gravity, of the white dwarf, and undergoes some hydrogen fusion to make some helium. Okay, so white dwarf gets some material on its surface. The gravity squishes that stuff until eventually the material on the surface can undergo hydrogen fusion and make some helium. Once it does that, once it gets enough to start kicking that off, it happens pretty fast. By pretty fast, I mean, you can see here it takes a couple days, not much. It doesn't blow up the entire star because these reactions are only happening on the surface. They're not happening in the core, they're only happening on the surface. So it gets really bright for a while, and then it takes it's like 20 days to drop this much, and then another 20 days to drop a little bit more back to where it was. So overall, like a little more than a month for it to get back to where it was. And what'll happen is that a nova is actually able to repeat because it blew up all that material, but this is still shooting material off into that white dwarf, which means the white dwarf is going to be building up that outer layer again. And then once that outer layer can ignite, it will ignite, do this brightness thing over again, get rid of all that material, and then wait for more material. Do you see how? So nova can be repeated, but supernova can't. In fact, there is an example the book gives, I cannot pronounce that, RS Ophiuchi, erupted in 1898, 1933, 1958, 1967, 1985, and 2006. So it ignited in each of those years as a nova because it gathered material, ignited that material, essentially burned it off, and waited for more material. Ignited that material, burnt it off, and waited for more material, and it goes in that cycle. Supernova, though, would just completely blow up the star. So now we know the difference between nova and supernova. Now let's look at that last thing that the introduction of the chapter brought us, that burster, or an X-ray burster. So we've been talking about white dwarfs this whole time, but rapid and explosive fusion of helium, not hydrogen, but helium, may occur in the surface of a companion neutron star, producing a sudden increase in X-rays called an X-ray burster. Notice how this is different. We're not talking about a white dwarf and hydrogen. We are now talking about a neutron star and helium. Right? So what happens is, in the same exact kind of process, a neutron star is orbiting one of its friends, and it gathers material, but that material is squished so hard that it instantly switches from hydrogen to helium, and eventually it gets this layer of hydrogen or helium. And eventually it gets this layer of helium to be able to fuse, and it has a burst of energy only on the shell of the neutron star. Not on the inside, but on the shell of the neutron star. In fact, there's actually also a little bit of hydrogen fusion going on there too. So you'll notice this picture looks really similar to this picture. The only difference is that that's a neutron star. And remember, a neutron star is a lot more massive than a white dwarf. So as it's sucking up this material, it squeezes it so hard that it instantly becomes helium. Then there's a small helium layer on that neutron star. And then the neutron star is pulling on the helium so hard that eventually, when there's enough of that helium, it will squeeze it so hard to be able to fuse. And once it does that, it releases a bunch of X-rays. And that's what we call an X-ray burster, because we pick it up as just a big old flash of X-rays coming from this binary star system. Notice this is a lot quicker than the other thing. This is a lot quicker than a nova. The flash happens in like a second, and then it fades in, what, like 10 seconds? Which is a lot quicker than the nova. The nova took like a day or two to show up, and then it takes about 40 days to fade away. This takes a second or two to show up and takes about 10 seconds to go away. It's just an immediate flash of X-rays like that. So why can a nova repeat its brightening but a supernova cannot? Hopefully you guys realize nova and bursters can be repeated because it's just burning off the shell of new material. But a supernova is exploding the inside of one of these stars. It's completely ripping everything apart. The nova is just igniting the outer shell of what's left of one of these dead stars. And then hopefully you guys picked up a nova is a white dwarf undergoing hydrogen fusion on its surface. An X-ray burster is a neutron star undergoing helium fusion on its surface. Okay. Nova is a white dwarf undergoing hydrogen fusion on its surface. X-ray burster is a neutron star undergoing helium fusion on its surface. And that's it for section 12.5. Kind of a long section, but this section is a little more difficult than like just the basic information on the black hole and stuff like that. So it took a little bit of extra time. Keep an eye out for your tests and your assignments and make sure you guys do all that on time. Otherwise, have a good rest of your day.